Suresh, would you please confirm with PRO once more? Just call him.
Uh, we are live, sir.
Okay.
Namaskar to Professor Buddhadev Bhattacharya and all our viewers attending this popular lecture from various digital platforms like Facebook or YouTube page of National Council of Science Museums or Facebook or YouTube page of Regional Science Center Guwahati or from the Google Meet. The topic of today's popular science lecture is mini bangs, mimics of the Big Bang. The Big Bang theory holds that the universe began as just a single point, then expanded and stretched to grow as large as it is right now. And it is still stretching. In this line, I would like to share one famous quote of Terence Daly, a famous author of fantasy novel. The quote is as the current state of knowledge can be summarized thus: in the beginning there was nothing which exploded. The analogy between the evolution of the early universe after the Big Bang and that of little bangs created in the lab is enhancing our scientific understanding of the universe. Large Hadron Collider (LHC), the most powerful particle accelerator even built, is expected to provide answers to a number of fundamental queries about nature, such as what are the fundamental building blocks of matter, what keeps them together, how did the universe begin. In the talk, Professor Bhattacharya will narrate how a situation similar to a nascent universe is recreated in the laboratory through ultra relativistic heavy ion collisions called mini bangs. He will also highlight Guwahati University's participation in various international collaborative programs in this field. Thank you very much for be a part of today's popular science lecture. One kind request from our viewers, there will be a question answer session after his lecture. So please keep with us. Your questions ready for the discussions. You can also post your questions and queries in message box during the lecture. So with these words, now I request our head and project coordinator, Sri Sujoy Mazumdar, for a formal welcome of our audience from all over India and today's knowledge resource, Professor Buddhadev Bhattacharya, Head Department of Physics, Guwahati University. Sujoy sir, the stage is yours now. You may please proceed.
Okay. Thank you, Suresh. And a very good afternoon and namaskar to all our viewers. It is indeed my great pleasure to welcome all the viewers in today's online lecture on the topic, as you told, that mini bangs is the big bangs, and hope it will be a very enlightening and exhaustive session. Also like to extend our sincere thanks to Professor Bhattacharya for giving his kind consent to become the speakers of today's online lecture. Welcome, sir, in our online platform. Namaskar, sir.
So, namaskar.
Okay, sir. It is very much important to explain why we team of Regional Science Center Guwahati, which is working under the Ministry of Culture, Government of India, arrange this type of online lecture session with eminent scientists, technologists, professors, doctors, engineers, etc. from all across India and abroad. Actually, NCSM, being the leading science communicator in India, always stresses the dissemination of scientific knowledge and inculcation of scientific temper among the masses. To honor this mandate, NCSM, throughout the COVID pandemic period, when the physical presence of visitors was not possible, until today, Regional Science Center Guwahati tried to remain connected with its client policy through its different online manifestations such as online hobby camp, science demonstration, exhibit explanations, lectures, etc. So today's program is one of the embodiment of the same. And I believe that there are a lot of scholars, viewers, they might be already heard the terms Big Bangs. And most probably the theory of Big Bang is our best guess about how the universe began, and it has happened nearly 30 billion years ago. So Professor Bhattacharya will tell more about it, details, and also we are eagerly waiting to hear from him about the Large Hadron Collider, and no doubt the most powerful particle accelerator ever built so far, which is expected to provide answer to a number of fundamental queries about the nature. In this regard, I would like to mention here that in the year 2019-20, NCS hosted Biggan Samagam, the first mega science exhibition in India in collaboration with Department of Atomic Energy and Development, Department of Science and Technology, Government of India. This exhibition had traversed our visitors through the world from micro to macro, unveiling the efforts of the international community in understanding the universe. Participation in the world's major mega science projects, where several developed countries are participated collectively. The participating global iconic scientific organizations were like CERN, FAIR, INO, ITR, LIGO, SK, TMT, etc. And during this process, we got a CERN's flagship state art traveling exhibition. Is named as Accelerating Science, and the exhibition traveled our units at Mumbai, Bangalore, Kolkata, and Delhi. So when we heard that Professor will also highlight Guwahati University's participation in two international collaborative programs, namely LHC and Allies of CERN and FAIR CBM of GSI Germany, it gives us the feeling of pride. We will definitely listen from him in details. But before that, let me introduce Dr. Buddhadev Bhattacharya formally to our viewers. That Dr. Buddhadev Bhattacharya is a professor and head of the Department of Physics, Guwahati University. He is MSc and PhD from Guwahati University, and his subject of PhD was nuclear physics. And Professor Bhattacharya is also a guest scientist of FAIR CBM experiment at the GSI and associate scientist of the LHC Allies experiment at the CERN. He has done extensive research work in the field of nuclear and experimental high energy physics. Currently, his research work includes investigation of the properties of the matter under extreme conditions found in ultra relativistic nuclear collisions. These research work are being carried out in collaboration with a large ion collider experiment. This in brief we call it LIC at the LHC at CERN, and the compressed varionoid matter experiment at GSI Germany. He also a member of Allies and CPM collaboration board. Recently, Department of Physics, Guwahati University has introduced a new course on the radiological physics. With his active involvement, he was the founder coordinator of the course. He is also a member of governing body and board of studies of physics for PG of various institutes like Assam University, Cotton University, Boroland University, Pratiksha Institute of Pharmaceuticals, etc. Professor Bhattacharya has produced a number of these and also published several papers in reputed international and national journals. He is also a referee of various international and national journals. He acted as the guest editor of two special issues of Indian Journal of Physics. He had been the General Secretary for consecutive terms of the Physics Academy of the Northeast. Well, with this word, I would now like to invite Professor Bhattacharya for the lecture. A request to our viewers, as Suresh already said, that at the end of his lecture, there will be a question answer session. So please be with us, keep your questions ready for the discussion. So without wasting further time, I am handing over the forum to Professor Buddhadev Bhattacharya to deliver his lecture. Please sir, the forum is yours now. Thank you.
So thanks, Mr. Kumar and Mr. Majumdar, for introducing me. It is indeed a great pleasure and privilege for me to deliver this talk from this platform as provided by the Regional Science Center of Guwahati. I convey my thanks to the organizers of the Regional Science Center, Guwahati. I also thanks to all of you who joined me for this session. I understand that you are quite enthusiastic about the scientific progress and science itself. Uh, Let me mention that this talk that I have prepared is very much in the line of the purpose of the Regional Science Center. So the whole purpose of this presentation is to motivate the young's mind so that in course of time they pursue physics as their professional career. I can assure all the young people who might be listening today that this mega project and the research in physics would be a very good alternative to the most common professions like say like medicine practice and say engineering. So I'll narrate later during my talk that how one can do the scientific research in today's world as a very nice professional career. So anyway, also at the end of my talk, I'll make a small video presentation of say 5 to 7 minutes, and thereafter, if there is any question, I'd be happy to give answer whatever I know. Thanks anyway once again to the organizers. So the plan of my talk would be that I'd first address rather that what are the fundamental building blocks of matter, and then I would narrate what do we mean by the gluon plasma, popularly known as QGP, then the big bangs and the mini bangs, and also I would introduce you with the two major global activities with the ultra-relativistic heavy ion collision programs of world. And then finally, I will make an attempt to narrate the university's participation in the two major collaborations, namely MSCLIs of CERN, Switzerland, and FAIR CBM of GSI, Germany. So with this, let me start. So it has been a quest for the mankind from long back to know that what are the fundamental building blocks of matter. So, for example, if you take an apple and if you divide it into two, you get basically two pieces of apple. Now, if you divide them into two more parts, then you get altogether 4 pieces of apples. You can still divide them and you get 8 pieces, 16 pieces, and so on, so forth. So before 500, say, or before 5th century, people, a general belief of people was that any matter can be subdivided into infinite number of stars. So you can divide matter for infinite number of times and you can get matter, the same matter. That was the general belief. But the first restriction was imposed in the year 400 BC by a famous Greek philosopher named Democritus. Democritus said that, well, you can divide and continue to divide matter for n number of times, but not for infinite number of times. After n divisions of matter, you will reach to the tiniest block of the matter, which you can never subdivide it, or which can never be subdivided. He named is atomos. So atomos in Greek means indivisible. So according to him, there should be something in the matter which cannot be further divided, and he named it as atomos. Only after 50 years, this idea of Democritus was challenged by none other than a more famous Greek philosopher, that is Aristotle. So in say 350 BC, Aristotle challenged the concept of Democritus of atoms. He rather put forward the idea that all matter consists of four elements, that is earth, air, water, and fire. This was something, I mean, in his view, it's something, a foolish idea that he put forward, challenging Democritus. But since it came from none other than Aristotle, when another French chemist named Antoine Lavoisier, he put forward the idea of what we call today as elements. According to Lavoisier, that the building blocks of all elements are basically, all matters are basically elements, and according to him, there should be around 65 elements. Now, Lavoisier at the same time made a profound decision. He mixed two gas, that is hydrogen and oxygen, in a bottle, and he could produce water. And thereby he proved that water is not at all a fundamental structure. But that was a huge blow to the Aristotle. 2002 years later of Democritus' atoms concept, the atom is again revisited by Dalton, that is in the year 1803. Dalton again revisited the concept of Democritus, that is the concept of elementary blocks of matter, and what Democritus named as atom. Now he said that every element, the smallest building blocks of every element is basically the atoms. And we know that in the this periodic table, altogether there are now say 118 elements. And it is believed that these elements have is consisted of the atoms, and these atoms could be of different mass and size, but the building blocks of all elements are fundamentally is atoms. So people then accepted this idea of this atomic concept of the building discovered is basically a part of atom. And then he put forward say an atomic model, what is we know today, the pudding model of J.J. Thomson. So the electron is believed to be, as of with this with the latest knowledge of modern science, we know that electron is a true fundamental particle. So in a sense, the credit of discovering a true fundamental particle goes to J.J. Thomson. Then in the year 1911, it was Ernest Rutherford who discovered from his famous gold foil experiment that atom consists of with yet another particle, what he named as nucleus. And he in fact came up with the true picture of the atom. What he says is that this nucleus is the heart of the atom. The nucleus is sitting at the center of the atom, and nucleus carry the most of the mass of the atom, and electrons are basically somewhere surrounding around this nucleus. So that was the Rutherford model of atom, which we still believe that this is more or less correct picture of the atom. So what fundamentally we know that atom is not at all a fundamental particle. Atom is not the building blocks of all visible matter. Atom itself consists of an electron and a nucleus. So in this context, let me just narrate one line from the Indian philosophy about the atoms. So what Indian philosophers believe that other than soul and space, everything in this world is made up of matter, which itself is made up of what is called Paraman. So the atomic concept is known to the Indian philosophers as well from the ancient time. And one interesting aspect of this Indian philosophy is that Indian philosophers believe that space is not consisted of the matter. It consists of something else. Now, in the latest concept of science, we call it the space is consisted of what is called a field. So let's not go in further details of this, but we here remember that an atom is itself a composite structure consisted of electron and nucleus. Now then the next questions come, if atom is not the fundamental building block, then what else? Is electron an elementary particle? Yes, the answer is an electron is a true elementary particle. Then the next question comes, is nucleus an elementary particle? The answer is no. The nucleus itself is again a composite structure which rather consists of a proton or protons and neutrons. So nucleus is not a fundamental structure. They are composed of protons and neutrons. So if you break with an all-powerful hammer the metal, first building block that will still retain the properties of that matter is a molecule. Just like if you take a block of ice and if you break it and reach to a molecule of water, then this molecule retain the properties, all the properties of water. Now, if you break the molecules further, what you get is basically atoms. So what is water is nothing but the 2 atoms of hydrogen and 1 atoms of oxygen. So if you break molecules, you will get atoms. If you still break your atoms, you will get the electrons. As I said, that electrons is a fundamental particle. So you get one fundamental particle, one building block of matter, but you get another composite structure, which is a nucleus. So if you still break up the nucleus, or if you still peep into the nucleus, what you see is you see that the nucleus is a collection of nucleons. You find that these nucleons are consist of basically quarks and gluons. So now, as of the most latest knowledge of science, we believe that electrons is a fundamental particle and a quarks is a fundamental matter particle. So a proton is consisted of 2 up quark and 1 down quark. There are 6, we call the 6 flavor of quarks. Don't take this flavor term too seriously. This flavor has nothing to do with flavor. It is just a type. So there are 6 types of quarks and 6 types of electron. Let me not introduce all these jungles of the elementary particle. So what I intend to tell you is that the true building blocks of matter are these 2 fundamental particles, that is 1 up quark, 1 down quark, and an electron. So whatever we can see, be it I, be it you, or a butterfly, or maybe a Taj Mahal, or the moon, the sun, the galaxy, or whatever you can see in the universe, all visible matter are basically composed of 3 fundamental particles. So this is 1 up quark, 1 down quark, and 1 electron. So what that the periodic table of chemist consists of 118 say elements. The periodic table of particle physics consists of only 3 particles, only 3, that U and D, and all these 3, only these 3 consist of, can make you all the 118 elements, and all these 118 elements can make you all the visible matter that is seen in today's universe. So we understand that the true fundamental building blocks are quarks and electrons, up quarks and down quarks and electrons. The other quarks are usually not present in the nature. They can be produced under a very special condition. So now next questions come that okay, you can take out a proton or neutron out of a nucleus. Similarly, can you take out a quark out of the hadrons, that is out of protons and neutrons? You can get free electrons. You can get one fundamental particle free in nature. You can get it electron anywhere or everywhere. We are almost in the sea of electrons. Now, can you get a free quark in nature? The answer is no. You cannot get a free quark in nature. So naturally, the question comes, why we cannot see a free quark in nature? It is because of the very nature of the strong interaction. So what happened? We know that the charged particle, we are aware of what is called electrostatic interaction.
Sorry to disturb you, sir. Sorry to disturb you. But PPT is not means visible. Something else is visible. So please check, sir.
Okay.
Sorry to disturb you.
No, it's okay. But other people are.
It is visible. I think someone has shared. I think some other person has shared. PPT is visible.
Some other person has said WhatsApp like this thing. So
no, it could be a local problem.
Someone has done this thing. So please, who has did it, please remove your slide, please. It's a request to you who has done this thing. Please remove your slide.
Yes, it is something Zudirika.
Yes, Suresh.
yes, now it's I think it's okay.
सर one more request सर, थोड़ा सा आपका हेड कट जाए व्यू में, आप थोड़ा सा आपको कैमरा के थोड़ा सा.
Is it okay?
Now it's
Yes,
okay. Now it's okay.
Now it's okay, sir. Please carry on, sir. Please.
So we are here that now we understand that the true periodic table does not consist of 118 substructure. It rather consists of only three fundamental particles. So now we are asking the question that can we see a quark in the nature? The answer is
sir?
Yes.
Hello, sir. Neelam sir here. Sir,
Yes.
you have to again present, sir. PPT is not visible. Use present again, sir.
Just a minute. Wait a minute. Just check it. The other people are seeing it.
Yes, sir, it is visible. Maybe on their screen it is not pinned up, sir.
Mhm.
Sir, PPT is visible.
Yes, sir, it's visible.
Sir, it's
Pin it, then
They have to pin it, sir.
Sir, it's visible.
Okay.
Okay, sir. Now it is visible, sir.
Now,
Okay.
sometimes what happens? There is a network issue with individual, and then it becomes static. So anyway, so that way, okay. So now the question is why we cannot see a free quark in nature. So that is because, as I said, it is because of the very new nature of the strong interaction. Now here we introduce a new type of interaction. It is a completely new concept which was not known the mass. People used to know about the two fundamental interaction, what we call the gravitational interaction and then the electromagnetic interaction. Now when you brought the picture of quarks, so you bring a new fundamental type of interaction, and that is called a strong interaction. I'll come to strong interaction later, but let us just look into what we call the electrostatic interaction or electromagnetic interaction. We all know that if we place two charges separated by a distance, two electric charges separated by a distance, then we know that if the charges are opposite charge, then they will attract each other. If the charges are similar charge, they will repel each other. And if force of attraction or repulsion is inversely proportional to their distance between them. If the distance is small, the force of interaction will be large. If the distance is large, the force will be small. So force varies like this. So it is an inverse variation. Now we also know that the field of flux line diverges from the positive charge, and it will converts to the negative charge. So this is what we know about the electromagnetic interaction. We also know that why with the distance the force decreases. We call it what is called the screening of electric charge. There is a polarization of the medium, and electric charge got screened, and that's why there is an increase or decrease in the force of attraction or repulsion with the distance. That knowledge we have. Now here things are a little bit different. Here the force is not between the color charge. Not between the electric charge. So you introduce a new concept of charge. You have electric charge, let it be there. Electric charges are there. But in addition to electric charge, the quarks have an additional charge. That additional charge, we call it color charge. This color, has nothing to do with don't take it by name. That color is a physical name of the charge. This has nothing to do with our day-to-day concept of color. It is another form of charge. Just by chance, it was named as color charge. And then that the interaction between the strong interaction between two quarks is through this because of their color charge. It is not because of their electrostatic or electric charge. So, and then we know that electromagnetic interaction takes place through the exchange of a field particle, what we call photon. Here the exchange particle is what we call gluons. Now there is a fundamental difference between a photon and gluon. Both are massless, that's fine. But the issue is that photons are basically chargeless. So in a sense, the photons, whenever a photons come to very close to another photon, not interact. So photons, people look it like that, the photons are a little bit unsocial. They do not interact with, but these gluons, they carry the color charge. As they carry color charge, the gluon-gluon interaction is possible. And the one gluon interact with another gluon. And because of this gluon-gluon interaction, the field line do not diverge. The field line, because of this gluon-gluon interaction or attraction, the field line converges. And as a result, so they looks like something like ropes. Now, the nature of strong interaction is that if you want to take, say, one quark from the vicinity of the others, we know that the quarks they are combined into to give you the structure of mesons, and they combine in three to give you the structure of baryons, that is protons and neutrons. So inside a proton or neutron there will be three quarks, and inside the mesons there will be two quarks. Now if you want to take one quark out of the vicinity of the other, so you have to apply force, and the more you apply force or the more you try to take them apart, they become more tightly bound. So you have to apply even more forces. Now if you apply more force to take them away from each other, you need to they become more bound, and then you need to apply even more force. So it's something like as if that you are stretching a string. If you pull a string, you have to exert some force. Now if you want to pull it further, you have to exert more force. If you want to exert even further, then you have to apply even more force. So it's something like this type of things is happening in case of strong interaction. So as if you cannot you cannot take away a quark from the other. But for the sake of argument, you say that I have applied enough force to this spring to take away one quark from the other. Then what happened? So what happened? If you exert enough force, then the string will broken up. So from here we understand that as the distance increases, the force of attraction between the quarks will increase. Now, if you apply more force and more force, what happens at some point of time, the string might be broken up. And the moment the string broken up, the energy will be released. And from that energy, following Einstein say E is equal to mc square, the quark, there will be the production of quark and anti-quark pair from the vacuum. Now, to this end, if you look at to this end, this string is broken now. Now, at one end, there is a quark, and at the other end is free. Now, the quark and anti-quark that will be created from the vacuum, the anti-quark will attach to this side of the broken string. So, as a result, you will again get a quark and anti-quark, that is, you will get a meson. And this side, on the right hand side, there is an anti-quark. So a quark will come and it will attach to this side of the broken string, and as a result you will get another meson. So you started with one meson, you end up with two meson, but you never, in the process, you never get a free quark. So this is what is called the very peculiar property, strong interaction. It is called the confinement property. So as if that the quarks are plugged inside the neutrons and protons. So you cannot see a free quark in the universe anywhere. You can understand that quarks are confined inside the mesons and baryons. So they are not free. So as if that this quark is present. Now the next question comes that were they never been free? Had they never been free in the nature? The answer is yes. They were in fact they were freed. Now that was only after 1 microsecond of the Big Bang. That is the 1 millionth second of the Big Bang, the quarks were actually free. So if this is the Big Bang, say t is equal to 0 time when the Big Bang took place. So just after 1 microsecond, the whole universe was basically filled up with quarks and antiquarks and gluons. And this, since the universe was extremely hot, of the order of say 10 to the power 12 Kelvin, at that temperature, they were running here and there. They are moving very fast. They are colliding each other. They had no time to talk to each other. And as a result of many large number of collisions, they almost created an equilibrium situation. And this is what is called the quark-gluon plasma phase of the universe. But at this stage, the universe was never being static. The universe, since its Big Bang, it was continuously expanding. It is expanding, as Suresh said during the introduction, it is still expanding. So the universe is expanding, and the more it is expanding, it is getting cooler and cooler. It is getting, cooler. And so when it cooled down sufficiently, this is called say Hagedron temperature. At this Hagedron temperature, what happened? The quarks has now cooled down. They have now little bit, lazier than their earlier situation. Now, when come too close to one another, they get bound. So they get bound by this strong interaction. And as a result, what happened? When two quarks get bound, they form mesons. If three quarks get bound, they form baryons. So this way, the quarks. So in a sense, it actually this has not taken place one by one. This has taken place suddenly, when the temperature has suddenly brought down to a critical temperature. And that critical temperature, as I said, is called say hagedron temperature, which is about say about 170 to 200 MeV temperature scale. So at that, which is almost the mass of mesons. At that temperature, the quarks has started recombining. The quark has started coalescing. What is this? This scenario is something you can believe that the formation of dew. You have a super saturated due to some the water vapor has little bit more cooler. It cooled down. And this QGP, when it expands just below the critical temperature, the quarks and gluons, which were freed otherwise, now got jailed inside the protons and neutrons. And ever since after that confinement, no quark have been seen free in the universe. So quark has permanently got prisoned inside the hadrons. And they are the end of the chance of getting any free quark in the universe. So the remaining story, we know that this hadron, now the universe will still cool down, and then at certain temperature, say 10 to the power 9 Kelvin, just after say 3 minutes, there will be these protons and neutrons will now recombine to give you the lighter nuclei. And then say at about 4,000 Kelvin, when the universe has cooled down significantly from 10 to the power 9 Kelvin to only 4 into 10 to the power 3 Kelvin. So about say 400 million years from the Big Bang, or sorry 400,000 years after the Big Bang, the atoms will be formed. And now you have nucleus, and nucleus is trying to pick up the electrons to become neutral, but the temperature at that point was so high that they could not retain the electrons bound with them. So because of the thermal vibration, the electrons were going out. So now, if the temperature comes down to a significant lower value, then at that point it is possible that an atoms will be formed. The nucleus will capture the electron and the neutral atoms will be formed. So immediately there will be a large number of formation of atoms of hydrogen and other lighter gas like helium. And then this gas will, due to their own mutual gravitational pull, they will collapse, and then the stars will be, the stars will be formed and the galaxies will be formed. We are not interested in the remaining part. Our interest is here, from QE to hadronic phase. We believe that this is a phase transition. And if this phase transition, and now what is hadron? Hadron is inside the nucleus. In our body, we have protons and neutrons inside our own body. We have protons and neutrons everywhere. So if we can free these quarks out of this hadron, can we see a free quark? Can we create a situation like this, which existed, say, about 15 billion years back from now? So so this is where we basically confine in these first two stages of the evolution of the universe. So now, so as we understand how to get QGP or free quark in this world, how can we get it? So there is only two possibilities. Either you travel back in time, you travel 15 billion years back in time and go to the QGP scenario. You can get QGP, carbon plasma free over there, or you wait for another Big Bang to occur. But I mean, both of these options are unrealistic. Neither you can travel back in time, nor you can wait for another Big Bang to occur. So then what is the way out? The way out is that the QCD, that is the branch of physics that deals with the strong interaction, it suggests that you can create quark-gluon plasma type of thing under a very special condition in this Earth itself. Now, questions come, what are those conditions under which you can create free quarks and gluons. Now these conditions are that you either compress a nucleus or heat it up. So you have to compress a nucleus. So what happens if you compress, then these nucleons, these protons and neutrons will overlap each other. And another important characteristic of strong interaction is what is called the asymptotic freedom. So the strong interaction is attractive at large distance, but when it comes to very small distance, then this force becomes little bit repulsive. So this is called the asymptotic property. So the repulsive in a sense that the strength of attraction will be reduced significantly. So it means that if you bring these protons and neutrons very close to each other, these quarks might behave as if they are free because of this asymptotic freedom behavior of the strong interaction. So each quarks will believe that it is a part of the other quark, and they will roam around freely. So you create a situation as if that was existed in the universe. The quarks and gluons start moving freely. They are no more confined inside the protons and neutrons. This is one way. The other way, you heat up. If you heat the nucleus is believed to be in the liquid phase. It's a liquid, a drop of liquid. So if you heat up, you evaporate nucleus. You create a gas of these protons and neutrons. And if you still further this gas of protons and neutrons, you can create quark-gluon plasma. So now the question is, okay, I am ready to heat it. You said that I am ready to heat the nucleus. Now up to what temperature you have to heat it? You have to heat the nucleus at a temperature of 2 into 10 to the power 12 Kelvin. That is 1,33,000 times more than the temperature that is available in the core of sun. So you have to heat up to that temperature. You have to heat a nucleus to that temperature, which is 1,33,000 times more than the temperature inside the sun. So you can imagine that to what extent you have to heat the nucleus to get quark and gluon free. So it is a very, very difficult task. And okay, fine. I will take the other path. I will not heat up. I will take the more easier path. I will just compress it, and then I will melt it. So okay, fine. If you want to compress, to what density you have to compress the nucleus, you have to create a situation which is 5 to 10 times the denser than the normal nuclear matter. So okay, what is the density? What is normal nuclear matter? I do not know. I know only the cell lead, which is the heaviest element perhaps, or next to heaviest element. So I know lead, I know iron, I know gold, I know silver, but I do not know the nuclear matter. So what is nuclear matter? So nuclear matter is 10 to the power 13 times more dense than the heaviest element on the earth. So you can imagine what is 10 to the power 13. You put 1 and then put 13 0 after 1. So you have to create a density which is 10 to the power 13 times more than the most heaviest element of the earth. So this is again a tremendous task to be achieved. At ease. So then how to create QGP? The answer is that you create mini bang in the laboratory. If you create mini bang in the laboratory, and how to create mini bang in the laboratory? You create them through ultra-relativistic heavy ion collision. You take two heavy nucleus, say gold or lead, and then allow them to move with the velocity of light, and then suddenly make a boom, collide them. They will just boom, and there will be debris. Out of that boom, you collect these debris and study these debris, and then you might realize that whether you could create a scenario which existed only after 1 microsecond of the Big Bang. So that is the task we do. So now this is indeed very difficult to do, but people have done it. So this is what exactly happened in a nucleus collision. So what happened? So these two nucleus will come from the opposite direction. So nucleus, otherwise they look like footballs. They are more or less spherical. But since they are moving with the relativistic energy, their length will be contracted. They will not look like now as a two sphere. They will look like as a two discs. And these two discs are nothing but the two clouds of neutrons and protons. So let them move with the velocity of light, almost with the velocity of light, and then collide. And then a boom will happen. And this boom is believed to be the same boom that happened 15 billion years ago. So you create a scenario which might be more or less similar to the scenario that existed long back. So, okay, I will come to that. So, and now to do this, there are two global facilities that have been developed across the globe. One at we call it at Brookhaven National Laboratory, BNL, at New York, USA, which is called Relativistic Heavian Collider, RHIC, and another at CERN, LHC. I will come to that. Now, what happens here? So you allow, say, these are small rings of accelerator, then a relatively bigger ring, and then the final ring. So let this is something like this will happen. So they will move. This is the linear part. It's a linear accelerator. It will lead the beam to this circular accelerator, and then a bigger circular accelerator, and then another circular. And then these two beams of gold nuclei will move in opposite direction with the speed of light. It's a tremendous energy they will carry, and they will collide at these four different points. And these are 4 different experiments of RHIC. And all these 4 experiments have different purposes. So they are called Phobos, Brahms, Phoenix, and Star. So you have gigantic detector you have placed to collect these debris. You collect them and you study their properties. And from there you make conclusion that whether QGP is formed, if formed, what is the nature of the QGP, what is the interaction between those quarks and quarks, and many things. I mean, a host of physics you can study over there. So in this, you can see that the velocity at RHIC, which is only, say, I should say, in comparison to LHC, it is 200 GeV. It's not in the scale of TeV. LHC is in the scale of TeV. So 200 GeV is giving you the velocity 0.99995 C. So it is almost moving with the velocity of light. Now go to the LHC. So this is the LHC. So this is even bigger cyclic accelerator, which spans over, this is Switzerland and France, over 2 countries. It is we all know that this is a 27-kilometer tunnel. So what is there? There are, 2 lead nuclei will move in opposite direction, and they will collide in these 4 different points. One is called ALICE, then CMS, then LHCb, and ATLAS. So at these 4, these are basically the 4 famous experiments of LHC. All these experiments have different purpose, have different physics goal to study. So the collision will take place, and there are again even still bigger detector you place to collect the debris and study them. So this is our ALICE detector, where the Goethe University is also a part of this, and you will be surprised to know that it is a very big detector and a complex detector. And these two red, the red portion is basically the magnet of the detector. And you will be surprised to know that the magnet, the iron that needs to be used for these magnets are more than the iron that was being used for the construction of Eiffel Tower. So the iron that are used is more than even the iron used in the Eiffel Tower. So these are such a big, gigantic detectors. So then this is the picture of, as I said, these are 2 nucleus. They are coming in opposite direction. They will collide, and in the overlapping region, the entire energy momentum that has been carried by these 2 beams will be dumped. And because of the dumping of such a huge amount of energy, you create a quark-gluon plasma type scenario. So you might have, so this is here. So you have, so this is your, on the right panel, this is your, the evolution of the universe. So here you create QGP. This is your QGP phase. Now this QGP that you have created in CERN, say, or in RIG, they will expand. Just like the universe expand, and just like here they coalesce into hadrons, they recombine to give you the hadron. Here also they will recombine to give you hadron. Now the complexity of the experiments are, you started with 2 clouds of hadrons, and you are getting back again hadrons only, thousands of hadrons only. So now you have to understand that by studying these hadrons, you have to understand if a QGP is formed or not. Even though you can produce QGP, you cannot study them directly because it will exist only for, say, 10 to the power minus 22 seconds. Even if quark-gluon plasma moves with the speed of light, which is only 10 to the power 8 meter, so you can imagine that if time multiplied by this velocity, what distance they can travel before they coalesce into hadrons. So it is not possible. You can, at best, you can keep your detector at best, say, 1 centimeter away, 1 millimeter away, even 1 micrometer away. Still you cannot get a free quark, even if it moves with the velocity of light to reach to your detector. Before that, it will coalesce into hadron. So you cannot get hadrons free in nature or even in the labs. But by studying this, you can, without any doubt, you can say that yes, QGP is formed in between. And then you can also say that exactly what is the nature of the QGP. Is QGP like a gas, or is QGP like a liquid? Is it a liquid like just our tap water? You can say all this information. You can gather all this information by studying all this produced hadron. So, as I said, that these are, so what you can say, now you have traveled time in back. We are here. We are now at 10 to the power 18 seconds away from the Big Bang. And you have traveled back in time, and you have reached in the quark-gluon plasma. That is in 10 to the power minus 6 seconds. So, we have traveled time in back, and we have reached to, or we were able to produce quark-gluon plasma. Now, as I said, that they will immediately coalesce into hadrons, and these hadrons will come out of the interaction center. So this is a simple picture we have taken in our own lab it's an emulsion picture where only this is a nucleus. This is a krypton nucleus coming. This thick line is a track of krypton nucleus, and it then collide with a silver nucleus. And since it is low energy collision, there will be only 50s, tens of, or say hundreds particles that will be produced. And this is a real RIG event. You can see that there are thousands of events. There are thousands of events in one single event, and you have to study at least 200 or 300 millions of events. So you can imagine, if this is the complexity of one event, what would be the complexity of 200 million or say 50 million events? You have to study each and every track of this. You have to follow each and every track and then study them. And then you have to either you find it useful for you or reject it. So this is an extremely tedious job. And this extreme tedious job are done by our students even here at Goethe University. I will show you some of our results later. So this is, you can imagine that how gigantic detectors are being installed over at RIC and LHC. So this is Atlas detector, and these are the two hostels of CERN building, which are say about 7-story. And you find that the Atlas detector is even taller than a 7-story building. So you can imagine that, I mean, how big the experiments are. And this is the complexity of the Alice detector, this Atlas and CMS are maybe even more complex. So we understand that experiment at LHC are big, they are heavy, and also took a long time to design and develop, and it involves a lot of money. It's millions of dollar of money. But then, okay, how to know that? As I said, that you started with hadron, you end up with hadron. Then how do you know that QGP was indeed formed? So what is called is that there is some smoking gun evidences. Now, what is smoking gun evidences? Suppose that you were sitting at your cabin on one nice day. You were just like normal other days. You were sitting in your cabin and doing your works. Or suppose you were sitting in your classroom and your madam is taking classes, and suddenly you see that you heard that there is a firing of gun. And immediately you rush out of your room, and you see that on the corridor there is a person who is sitting, fallen on the corridor amidst a bloodbath, and another person who is holding a gun, and smoke is coming out of the gun, and there is no third person in the entire corridor. So now, you have not seen that the man who is holding the gun has actually fired. When he fired, you were not there. You have not seen him while he fired the other person. But you have no doubt that it is that man who is holding the gun who has fired the other person. So this is called the smoking gun evidences. So that means that even though we do not see the quark and gluon free with our detectors, but there is no doubt, there is no shock that you have really produced quark gluon plasma in the process. So that's called. Now there are a number of, actually all this whatever I have said is not my field of research. My field of research is only in this here, that is studying the signatures of QGP. That if QGP is formed, if it has formed, what is its properties? So there are a number of signals that say without any doubt that QGP was formed in the process, and these are called Jepsi suppression, strangeness enhancement, elliptic flow, net baryon, and net charge fluctuation, jet quenching, etc. So these are some technical talk. So I have not, I will not discuss all of them or any of them. But if you insist me or if you ask me, then I can discuss one or two during the question and answer session. So that's all about that. Now let me tell you a little bit of our activities of Guwahati University in the as far as the heavy-ion collision is concerned. So GV, as I said, that GV is a part of two major international collaboration, namely the Large Hadron Collider at ALICE, and then we are also a part of this is a fair CBM experiment of GSI Darmstadt, Germany. So this is the MOU we signed with CERN authority. So this is our register who signed. This is the Sergei Bartolozzi, who was the then director of research and computing of CERN. This is myself as the leader of the GU group. And this is Paolo Giubilino, who is the then spokesperson of ALICE. Now Paolo is now the director of GSI Darmstadt. So he was the spokesperson. So the MOU was signed at IIT Bombay. This was a picture taken at IIT Bombay. The man who is just out of frame is actually Federico Antinori, who was the physics coordinator of that time. Later on, he became also the coordinator of ALICE spokesperson. The other person is the Professor Y.P. Byogi, the director of IOP, former director of IOP Bhubaneswar. Then he is the third person is the Shivaji Raha, the former director of Bose Institute. In fact, Bose Institute, Guwahati University, NISER, Bhubaneswar, and IIT Indore. These four institutes together joined in the ALICE in the year 2013, and the MOU was signed in IIT Bombay. So this is, as I said, Dr. Raha. This is myself. This is Paolo Giubilino, the then spokesperson. There, Dr. Vikas Sinha. He is the then director of Variable Energy Spectroscopy Center, Calcutta, and the director of Shah Institute of Nuclear Physics, Calcutta. A Padma Vibhushan, also a scientific advisor to Prime Minister, a big shot of our country, and one of the pioneer of starting the what we call the experimental high energy physics or plasma activities in India. So he is a faculty of IIT Indore, and then the then spokesperson of ALIS, Tapan Naik, now science scientist, and he is the present spokesperson of ALIS collaboration, ALIS India collaboration, Vedant Das Mohanty, Professor Vedant Das Mohanty. So these are the various institutes which are currently the part of ALIS collaboration, like BCC SINP from Calcutta, Bose Institute, Aligarh Muslim University, IOP Bhubaneswar, Niger Bhubaneswar, Punjab University, Guwahati University, Indian Institute of Technology Indore, Rajasthan University, Jammu University, IIT Bombay, and BARC. So this is, and 2 or 3 institutes will join soon this collaboration. So from the entire Northeast, you can see this Guwahati University is the only organization or only institute which is taking part in any experiment of CERN. So we are there in ALIS at least. So fine. So this is the collaboration size. You can imagine that it's almost about 1,500 scientists, technicians, physicists, and engineers, and that constitute the ALIS collaboration. Because you need lot of engineers to build up the detector. You need lot of technicians to help you out. You need lot of scientists to handle the detector as well as the data that you collect. It's a petabyte data. It's a very big, huge data volume, and you need also physics to analyze the data. So it's a big collaboration. We will be, at that time we are not there, but if a recent photo is taken, we will be somewhere here in the public. So then we again sign another MOU with, as I said, with FAIR CBM. This is the signature of our register, and Guwahati University signed MOU with FAIR CBM. So this is the construction. I will show the video on FAIR CBM because of the reason that, well, FAIR CBM is only 1.1 kilometer diameter tunnel, but and LHC is 27, and the next LHC is coming 100 kilometer. So you can imagine what is going to happen in next coming years. But I will show this new facility, which is now currently in the building stage. It is in the building. It is now in make-up stage. It is under construction. It will give fast beam expectedly in the year 2026 or somewhere 2027 or 2028. So it's at least 6-7 years from now. So the young people who might be listening, for them, the fair could be a very good destination. I will show you and talk later. So this is our students are regularly visiting CERN. They are participating in ALIS experiment in as a shifter. You have to give some service to the ALIS because it is a big collaboration. It cannot run by itself. It needs contribution from all the collaborators. So Noor Hussain, who might be listening to this talk, he is at CERN taking shifts. He is Pranjal Sharma, who is also listening this talk, who is also currently working with me and is giving his shift duty at CERN. This is ALIS control room, inside the ALIS control room. This is myself in the ALIS control room with Elena Botta of INFN. I acted as a ALIS as a shifter, as a shift leader of ALIS run. Here myself is seen with Paolo Giubilino. He's a nice gentleman with more than 6 feet height. So, and this is what we make. We arrange. We hold Guwahati University held the ALIS collaboration meeting a few years back, and the man with Gamusa is is actually Federico Antinori, who was the spokesperson at that time. And the man with the black suit with the Federico is Dr. D.K. Srivastav, the director of Renewable Energy Cyclotron Center. And the man who is sitting here is the current spokesperson of Alice India spokesperson. And only the day before yesterday, I came to know that he has been appointed in a very big post now by the government of India. So he is taking a lot of responsibility. He's a young man, but taking a lot of responsibility. So we have been given some fund by DST, which is of the order of say 3.5 crores. And with that fund, we have developed some facilities here at Guwahati University. We have developed high performance computing cluster, which we use for simulation work for predicting this nucleus collision event by simulation and then study them. Also, we have developed a facility for testing the detectors using some gas mixing type of unit. And these are something. And then we are also taking in the ALICE data analysis. This is one of the result of our Guwahati University's result of data analysis. This data analysis was done in collaboration with 5 other institutes. It was a work of altogether 6 institutes, Guwahati University. It was a work of Noor Hussain, then INFN Bari, Italy, then Mexico City, then Bologna University, then Turin University, and Lund University. These 6 institutes joined hands to analyze this data and got this result. This is an maybe if I get an good opportunity, sometimes I will discuss all things. But I would just say that this is a beautiful picture of collective behavior of the matter that has been produced in the lead collision. Now, if a new phase is to form, if a quad plasma has been formed, then this plasma should be in a phase of, if it is to form a phase, it should be in equilibrium. It should create an equilibrium situation, and the matter should move with collective motion. This is a clear signature of collectivity, which I will discuss at some other time. Then, generally, what happened that generally the small systems like PP collisions are studied as a background event, just to compare the heavy ion collision with the trivial collision. But then there is with the increase of energy of that of LAC, some peculiar behavior could be registered with the ALICE data. And we could see that even you do not expect that a QGP like a matter would be formed in PP collision, because in proton there will be only 3 quarks. So 3, 3, 6. With this 6 quark, you cannot make a QGP like scenario. But then it is observed that we can get some collective behavior even in the PP collision, in the central PP collision, which is almost equivalent to peripheral lead collision. So people have now started thinking that if something like phase transition has also taken place, or if the matter has really given some evidences of collective motion, even in the smallest system like PP. And for this analysis, Guwahati University joined hand with the University of Copenhagen, then Turin University, University of Greece, and Lund University. So these 5 institutes analyzed this data and produced this result. And this is the earlier result was published in Physical Review C in 2020, and this result was published in European Physical Journal C 2020. Then we have been constantly doing the referee work, the review work of ALICE paper. We are being asked by the ALICE editorial board to review a number of ALICE paper that has been sent for publication, and that has finally been published in different journals. I'm happy to let you know that one of the papers that has been sent by Alice collaboration for publication in Nature was reviewed by us, and that paper was finally accepted in Nature and published in Nature as a new laboratory to study hadron-hadron interaction. That was published in Nature. So we are also involved in the say reviewing work of Alice publications. So we are doing this. We have reviewed a number of papers like that. I have cited a few. And these are a few recent publications that we have published out of our important recent publication I have cited here that we published in different reputed journals. This is one, I think, Koilan, who is now a faculty in Boroland University. We have published a paper in Physical Review C, then Nuclear Instrumentation and Method, then Nuclear Physics A, Physical Review C, and then Physical Review C. We have published number of papers on heavy ion collision. So this is what I would like to conclude here. So this is a structure in between the two CERN hostel that I have shown you while comparing the Atlas detector, and this is the Nataraj statue, and this is the only religious statue that I have seen inside the CERN, and there is no other religious statue inside the CERN. So thanks for your patience. Thank you. So let me, before I end up, just let me play this 5 minutes video particularly for the students to motivate the young minds to pursue physics, to take up physics as your profession. Just a minute. Yeah, just wait a minute. I'll be opening up my another browser and then I'll start it.
Sure,
just
sir. Please, sir. Please.
Isn't it? Could you see it? Okay. So I'm playing. Just let me see if it happens.
Matter, the stuff the world is made of. Matter was created in the universe, but how exactly did it come into being, and what are its properties? The FAIR Accelerator Facility in Darmstadt. Here, scientists want to unravel the secrets about the structure and evolution of the universe. Giant planets, stars, and stellar explosions subject matter to extreme conditions, such as very high temperatures and pressures, and these extreme conditions can be reproduced at FAIR. FAIR is the universe in the laboratory.
We have a number of scientific discoveries which already are sure to be made here. But I know from experience that whenever you provide scientists with such a big jump in the capabilities of a scientific instrument, what you get are surprises. We know that there's going to be discoveries. They are planned, there are measurements that we know will produce results, but it's the surprises I am after.
FAIR is the only facility of its kind in the world. It consists of a ring accelerator with a circumference of 1,100 meters and a complex system of storage rings and experiments. FAIR will produce beams of ions and antiprotons of the highest quality and intensity.
These are unique opportunities worldwide, and this is why researchers from all over the world, already 53 countries, are seeing this as their laboratory of choice for their research in the coming years.
To bring the universe into the laboratory, scientists at FAIR have organized themselves into 4 experiment collaborations. They want to find answers to questions like, how are heavy chemical elements created in stars and stellar explosions? In what form does matter exist in neutron stars, the extremely compact remnants of supernova explosions? How can antimatter help us understand the mass of matter and the strong force? Which fundamental symmetries define our universe? What are the properties of high-density plasmas that occur in the interiors of large planets? How can we use particles to heal diseases? And how can we protect astronauts against cosmic radiation? Can we use ion beams to change specific properties of materials? The collaborations have developed cutting-edge measurement methods and techniques for their research. They will measure the particle collisions generated by the accelerator using detectors, some of which are as tall as a building. Vast amounts of data will be accumulated during the experiments. This data will be saved and evaluated by one of the most energy-efficient computer centers in the world, a new ultra-high performance computer center called Green IT Cube. The computer racks are cooled by water using a patented system that was developed in-house. Just one example of the many innovations that have resulted from basic research. FAIR will help accelerate the development of vacuum technology, magnet technology, and superconductivity. The FAIR facility is being built at GSI, the Helmholtz Center for Heavy Ion Research, a world-renowned research institute that has more than 40 years of experience in building and operating accelerators. At GSI, scientists have discovered 6 new chemical elements, for example, and developed a tumor treatment that uses heavy ions. FAIR is being built by an international partnership of 9 countries. The biggest contribution is being made by Germany. More than 3,000 scientists from every continent will conduct research here, and they are already preparing the experiments of the future.
One of the greatest things of this laboratory is that it is a unique opportunity for learning. So we have people coming from all over the world, from South Africa to Japan, here to learn not only science, but all sorts of different advanced technologies. And for us, this is a fundamental function of our laboratory, that we provide training and opportunities for growth to young people in science and in engineering, and that this then goes back to society at large, and it's our contribution to the future of the world.
Thank you. Yeah.
Thank you, sir.
So it's my pleasure.
It's Suresh.
Yes, yes.
Yeah, will you start, please?
Yes, yes. First of all, on behalf of Regional Science Center, I would like to convey my sincere congratulations to Guwahati University for their such outstanding collaborations, such outstanding reviews, and such outstanding outputs in the field of this Big Bang or LHC or such collaborations. Thank you. Congratulations to Guwahati University, Physics Department, and sir, especially to you. And now we are receiving some questions, sir. First question, may I proceed, sir?
Yeah.
Yes. Importance of collaborations in research in today's time, the time of means such big science projects. The
Yes.
importance of collaborations.
Yes. Yes. It's a nice question. No, if you really interested to do a cutting edge experiment today, so you can do it alone. So there are, I mean, first thing is it is very difficult to do it with a tabletop experiment. This is number one, and at the same time, you need a lot of investment. So collaboration is needed both for financial aspect as well as for academic aspect. Academic aspect is more important in the sense that today both the experimental physics, be it computational physics, be it theoretical physics, it has gone to any level, and it is very difficult to do yourself alone everything. You cannot do. So you need a team of people, and you have to learn that how you can work with a team of people. So collaboration is very important. I believe that these are ALICE or CBN, where India is participating in a very large way. It is very good opportunity for the Indian scientists to participate in this kind of experiment.
Thank you, sir. And one more question, sir. He wants to know more about antiparticles.
Antiparticles are basically the particles of, you can say, the same mass, same charge, same mass, same spin, but having different charge. It is just the antibody of the particle. It will behave exactly in the same way. It will follow the same physics rule, but it might behave in a different way. Just it will bend in a different way in a magnetic field if you place it. The antiparticles, you can consider the positron as an antiparticle of electron. So positron has the same mass as electron. It has the same spin as electron, but it has different charge. So this has come basically from what is called Dirac negative energy concept. But they do exist in nature. They are real objects. Even though they are less in number, there is lot of work going on to know that why our universe is consisted of only matter but not antimatter. Where all those antimatter has gone. Which is believed that initially at the beginning the matter and antimatter are available as often as the matter is. But at some point of time antimatter has suddenly vanished. What is the reason? This is one of the biggest quest of this heavy ion collision to know that why the universe is made up of only matter but not antimatter.
Thank you, sir. And one more question. He wants to know the impact of the outcomes from the projects like LHC. The impact of the outcomes of the big projects like LHC in our day-to-day life.
It is again very important question. When Faraday discovered electricity, he was very enthusiastic about his discovery because he knew the potential of that discovery. Then he brought the finance minister of England to show him about this famous discovery. He exhibited the experiment showing that electricity is produced. Then the finance minister asked, "Okay, I have what to do with this." Then Faraday said that, "See, this is a nascent child only. It is a child. You do not know that when your child will be a full-grown person. I mean, he could be a prime minister of the England. You do not know what is his potentiality." So I imagine that this discovery has immense potential for the future. That was his answer. Now, to be very specific, that whatever you do not know that Higgs is discovered in CERN. You do not know that how this Higgs will be technically utilized in the coming days. But I mean, to make him more happy, I will give you a direct application of such big, what I should say, that exercise of CERN. Today, that you are doing www, that internet, and all this has come from CERN only. The first internet was developed at CERN. So, and that was developed only to transmit data from one floor to another floor. And now you can just put and search in the Google and get any answer that you like to do. This is one direct application of the exercise of CERN. And the second is that the everybody has now in his hand that smartphone. This touching screen technology has been developed by CERN scientists again. So I could just show you two. There are many more. Even the cancer patients are being treated with particle accelerator. That was, your BBCI, Dr. Dula Cancer Institute has a number of particle accelerators to treat cancer. So all these are coming from this type of activities only. So they have immense practical applications. Now, suppose about fair CBM. Fair CBM, they find that the rate with which the data will be generated, it is the C++ programming is not sufficient to handle that data rate. So they are developing a new language for analyzing CBM data. So you will soon get in the market something which is not C++ but more efficient than C++. So a lot of things coming from these institutes.
Thank you, sir. And one more question from Prathapatin Sarma, and he wants to know: is it possible for an existence to exist with only up and down quark without any electron?
No, I don't think. Unless because it is the distribution of the electron that give you different material. Elements. Building block wise, hydrogen and oxygen are not different. Hydrogen is consist of up quark, down quark, and electron. Oxygen is also consisted of up quark, down quark, and electron. It is because of the distribution of the electrons that gives the chemistry, and that gives you the elements, and then so it is not possible. It is not possible. I do not believe so.
Thank you, sir. And one more question. He wants to know why symmetry is so important.
Symmetry is important. This is symmetry because you know that symmetry is broken. And this CP violation, this is called charge parity symmetry breaking. That CP violating symmetry breaking, as it is believed that CP violating symmetry has given birth of matter. Had matter and antimatter were same in number, so today's universe, you, me, or nothing could existed. The universe were filled up of only radiation. It is because that CP symmetry was broken at some point of time. The matter dominated over antimatter, and therefore matter and antimatter annihilation could be stopped. Since matter dominated, you and me, the universe would exist. And so it is important. I mean, symmetry is important for physics laws. Yes.
Yes, thank you, sir. And again, one question from Pratha Pratim Sharma. What is the life of a quark? What is the life of a quark?
Life.
Yes, sir.
Life of a quark means, see, the down quark can change its flavor. I exactly do not remember what is the half-life, or does quark have any half-life, but quark life will be changed. A quark can change from up quark to down quark. So quark can change its flavor. That much I can.
Thank you, sir. And one more question from Nari Pakanik. Sir, is the neutrino detected in lab? Can it interact with quarks?
First part I can tell you with definity that yes, neutrino has been detected long back. The famous Rains and Kavan's experiment that they did with antineutrino coming from nuclear reactor, and they allowed to react with water, hydrogen of the water, and then can detect the neutrino. That has been done long back. Then afterwards, there were famous experiments like Davy's experiment. So neutrino has been experimentally detected, but can it interact with quark? I have not seen any report on that. I cannot tell you at this moment.
Thank you.
Since neutrino is basically mostly almost non-interacting particle because it has neither charge nor almost no mass, little mass, so it is almost uninteracting particle or non-interacting particle.
One more question, sir. What are the limitations of Big Bang theory according to you?
I am not a cosmologist, so there could be many that Big Bang theory. What could be the limitations of Big Bang theory? I just cannot remind right this moment. But there should be. I mean, there should be. Yes, one. Okay, I can remember. One limitation is Big Bang theory cannot explain. First thing that it cannot explain that why the bang itself took place. What is the reason that at some point of time that point exploded? That reason Big Bang cannot provide. Further, Big Bang cannot give you anything, any information about the universe beyond that explosion. If the point was there, how come that point came? So there must be something before it exploded. So Big Bang cannot provide you any information before the explosion. So this is the two major limitations of the Big Bang.
Thank you very much, sir. And we have also one limitation, time limitation. Yeah. So we have to just means.
Yes.
Okay.
Suresh, I have a question to sir.
Yes.
Actually, may not be it's very technical question. I want to know for the basically benefit of the students, or I'm not talking of the students who are doing the graduation or those who are doing the PhD under you, but little bit as you told me, this fair and other collaborative program, it will take much time, 6 years, 7 years time to work. So those who are young students, how they will get the chance in there? Oh, basically, what is the procedure? If a student right now he is studying at class 10 or 12 and maybe in the first year graduation, so what is the procedure to work on those iconic laboratory? If you explain for the benefit of the students.
It's very simple. I can assure you that it is much simpler than cracking NEET or JEE or even CE.
Okay.
It is so simple that just one can do it at ease. Now in India there is an examination called JRF. NET examination. So NET examination is done for two purposes. One is for lecturership job and another is called for research fellowship. Now if anyone, and this is not that hard, the way I have seen, the way the medical people take preparation for getting a seat in any of the medical college, even maybe in the Nagaon Medical College, one has to do say 25% of the effort that they are giving for that. If you give only 25% of the effort, they can click the JRF examination, and once they get the JRF examination, they can join any institute any top institute. Forget about if somebody may not like to join, say us. I don't. Okay, no problem. One can go to TIFR. One can go to BCC. One can go to say any other institute of our country, IISc Bangalore, and then those institutes are also a part of the collaboration. And I can tell you that Guwahati University recently, DST has become very strict nowadays in granting money. Now they are accounting for every rupee of money. So this year they have started a new mechanism of assessing every collaborating institute. They will give mark out of 10. And I have been told only yesterday by a DST people who is dealing mega science project. He informed that Guwahati University could score 8.5 out of 10 in the marking, and that marking was done by the top scientists of the country who have been appointed by the DST. And they said that as of now, only 2 institutes have been successfully reviewed. One is yours and one is Punjab University, and you scored more than the Punjab University.
Oh, great, sir.
So
one more thing, it has been seen that the people, young generation people are mainly looking for the engineering and doctor like that. So students becoming very less, those who want to opt their career as a researcher. So this Guwahati University, are you thinking for promotional, so that is more students coming to take up this basic science courses?
In fact, they should. No, this teaching and research is a very decent, profession. Yeah, if you now people now realize that medical profession is professional hazard. You have seen in TV and everywhere how doctors were beaten by the relatives of the patient. So, but we do not have that type of hazard as of now. So it's a nice profession, and if you are a scientist somewhere now, going for postdoctoral with a postdoctoral fellowship in any institute like CERN, GSI is a very small thing. You just do a nice PhD in any of these collaboration from any of the renowned institute who are in the, and then go for the PDF. If you do some genuine work, they will, and you stay there for 2 years and 3 years. Say 3 years. What you do is you earn lot of money because they will be paying you in terms of dollar. You convert it in rupee, you get lot of money. You create a good friend cycle who are doing cutting edge science. So you can retain that friendship with them, and you can pursue your physics for the years to come. So it is a nice profession. Young people should take. And see, in India, now we have 2 accelerators or 3 accelerators. One at Nucleus Science Center, today it is called Inter-University Accelerator Center, New Delhi. Then we have one at TIFR. And then we have one at BECC. Now all these accelerators are in MeV range, in 10 to the power 6 eV. Now world has gone to 10 to the power 12 eV in TeV. CERN is producing beam in TeV. So they are advanced in energy than us by million times. We are behind them in energy scale by million times. Now who should take up this challenge to become at par with them? It is the young people.
Right. Okay. Over to Suresh. I think there are some more questions. You may take some.
I think we can. I think we can stop it now.
Okay. I can say that it is a comparative new group who are working in right now Regional Science Center Guwahati. We are looking for this kind of